Okay, here we go. All right, let's go to. Okay, so just leading back towards what we talked about in the past, no, actually just a few minutes ago. So the problem with the superheterodyne receiver right now is that you will get two frequencies, two different carrier frequencies that get modulated or shifted down to where the intermediate frequency. One is the desired carrier frequency, and then the other, which is called the image frequency, which is 2 times the intermediate frequency away from the center. All right, so this is FC plus. Okay, so yeah, so you're going to have 2 different frequencies, and that's not good. So what we can do now is there's got to be a way to get the signal that you want, but then filter out the signal that you don't want. So what we can do is we can go ahead and put in a tunable bandpass filter. So remember what I talked about, tunable bandpass filter is not good. In this case, it is, and I'll talk about why that is in a minute. So what we can do is we can put a tunable bandpass filter right at the beginning so that we're at the carrier frequency that you want to extract out. You want to make sure that the image frequency, which is at twice the intermediate frequency from the carrier, you want to make sure that you eliminate any contributions of that frequency so that when you finally do this mixing, you just get the carrier frequency that you want. Okay? So you want to implement a tunable RF stage such that you get rid of your image frequency. Okay? All right, so let's go ahead and actually, so we're going to go step by step in terms of diagrams and see what this would look like if you decided to add in a tunable bandpass filter. In this case, I'd like to stress that it's realizable, and I'll talk about that in a minute. So, this is, this would be your frequency division multiplex signal, right? This is the desired one that you want, right? And then this is the image. So this is what you don't want. This is not what we want. If you didn't have this bandpass filter here, then what's going to happen is that these two carriers will get mixed so that they're both overlapping on top of each other, and that's not good. Okay, you want to make it so that at this frequency you want to make sure that that doesn't come into play. Okay, so what you'll do is you'll have a bandpass filter. Notice that this is realizable. So it's actually not as expensive. I'll correct myself now. It's actually not as expensive to make a tunable bandpass filter. It's expensive to make a tunable and then high quality bandpass filter where these the transition edges are very, very small. So this is realizable. So if you actually have a more realizable bandpass filter and then you can actually change where the center frequency is, then yeah, that's actually a lot cheaper to realize. Okay, so the point of this bandpass filter is to keep the frequency that you want, right? And then remove the image frequency. So what you're doing is you're applying a bandpass filter at the desired frequency that you want. And then the rest of this is just perfect, it stays the same. Okay? So when you decide to apply a bandpass filter, what's going to happen is that the spectra at the image frequencies, they're pretty much almost zero, right? So these are almost zero, right? You don't want them to interfere in the actual demodulation process, okay? So, oopsie, gotta go down. Okay. So now that we have this one, now what you want to do is you want to take this and you want to heterodyne with the local oscillations so that it's the carrier plus your intermediate frequency. And then you'll take this and then you'll plus minus 1055. So then when you actually bring it down, you're going to have a copy at 455 and then a copy at 1910, which we remove, right? So this is what we have. So remember, you have the 2 frequencies that are. So if you take a look here, this here is your image frequency. This is your image spectra, but the bandpass filter made it such that the contributions are very small. So this is approximately 0. Right, so you don't really hear it at the output. Okay, so you have and then the intermediate frequency stage. You go ahead and just filter it out. Okay, actually it's yeah. So you go ahead and filter it out, right? Again, so you don't have to really change it, right? So the reason why you still need this is because you still have other spectra. Like you could have there could be other spectra here, right? And so on and so forth. So the only reason why you have the RF stage is to filter out this component. This one goes bye-bye. The rest of the spectra stay the same, right? And then once you go ahead and heterodyne, you still have the other spectra you have to deal with, which is why you need this intermediate frequency stage to get rid of the rest of your signals. So this RF stage makes sure that the image frequency goes away, and then the IF stage makes sure that once you do the mixing, the rest of the frequencies go away. So you still need this in order to do the rest of the process, all right? And then you can make so this is ideal for now, and then you can try to. So what you can do is you can still make this as ideal as possible, but it's actually cheap to make sure that the frequency is fixed. But then if you make the frequency fixed, you can still make the electronics so that it approaches a bandpass filter as best as possible, right? You go ahead and filter that, and then the output would simply be this. And then you see here that the image spectra is very, very small. And then you demodulate, you bring it back down to your baseband, which is what we have here, and then you finally put that through your audio amplifier so you can actually listen to what the signal would be. Okay, so the only difference is this guy right over here. And we can make this tunable, but also we can make it realizable, where the pass bands or the transition bands are quite large. So you can make it a little cheap, right? To make sure that you filter out the image frequencies. Okay, so this is objective. So this is what we had before. So this is before, and this didn't work. So no tunable RF stage at the front of the receiver, but this is after, and this does work. So what this is saying is that you are putting in a bandpass filter right before you start the frequency mixing process. Okay. So what's the difference between here? Why is it so that even though we have a tunable bandpass filter, it still will work, even though we said in the past that it doesn't work because the tunable is very expensive. Okay. So this is what we had before. So before, when we actually went through all the heterodyning and all that, this is when you wanted to just simply put a bandpass filter around the signal that you wanted and extract out that particular signal. So the main function, this is before, was to make sure that you reject all of the frequencies except for the channel that you want to receive. So that was the purpose of the RF stage. This is before. Okay? So what you're doing is you apply a bandpass filter around the signal that you want to extract, and you demodulate, then you put it through your audio amplifier, and that's it, you're done. Okay? But this was non-realizable, mainly because to have a high-quality bandpass filter and on top of that tunable, it's actually very expensive. You have to choose one or the other. You have to make it tunable, but the filter is pretty crap, or you want to make it high quality, but the center frequency is fixed. If you want to have both, then it's very expensive. You want to choose one or the other. So we choose a tunable bandpass filter that has a crappy filter response at the beginning, and then in the later end, we have a very high quality bandpass filter that is a fixed center. So that there's two sides of the coin that we're realizing here. Okay, so therefore, it had to be a tunable bandpass filter with a high gain, highly selective over a wide range of frequencies, which is not what we want. That's actually quite expensive. Okay, now this is after. So instead of doing what we talked about before, what you're going to do now is the purpose of the RF stage when you're doing the superheterodyne receiver is to make sure that you filter out the image frequencies. So basically you want to reject image signals. So this is what you want to get rid of first. There's still going to be other spectra. There might be something here, there might be something here, for example, right? You want to get rid of the frequency spectra that is specifically centered at the image frequency. You want to leave everything else intact because the intermediate frequency stage, whatever, that stage, will filter out the rest of your signals. But the purpose is to get rid of this image frequency so that when you're doing the mixing, you don't listen to that interference when you're finally down converting using that local oscillator frequency. All right? So the tunable RF stage can be a simpler bandpass filter. This is realizable. That's totally fine. So we can actually make this tunable, but we can also make the frequency response a little more crappier. So that the electronics are simpler and it's actually a lot cheaper to do. So we can actually go ahead and do it like this, so that the image frequency, the spectra of the image frequency kind of get diminished, or the magnitude is actually very small. Okay, so that's the reason why you want to put a tunable RF stage before the heterodyne and before the mixing process, but it's actually a lot cheaper to realize. So it's actually a good way to go here. Okay, so here are some practical considerations. Since the image frequency is at twice the intermediate with respect to the center, right? If you decide to increase the intermediate frequency, right? So instead of making a 455, you can make it larger, like maybe a megahertz or maybe 9 kilohertz, for example. If you make the intermediate frequency larger, this means that your tolerances for your pass bands or for your stop bands, they can actually be larger, which will let you make your electronics more cheaper. Okay, so better attenuation. This means that the transition band is larger, therefore cheaper bandpass filter is possible. Right? If you make it larger, this means that you can actually make the span, you can actually make the transition band a little larger, and that's actually a lot more cheaper to realize. Okay, so practically you want to make the intermediate frequency as high as possible so that the bandpass filter that you design right before you start the mixing, the tolerances or the pass bands and the stop bands, they actually will have a little bit more flexibility, so that makes it a lot more cheaper to make. Okay, so that's something that you want to consider. But sometimes you can't, because 455 kilohertz is the standard intermediate frequency for AM signals, and that unfortunately you can't make higher, so you'll have to do something else. Okay, so there are other requirements you have to take into consideration, such that you also have a tunable local oscillator, right? When you want to tune into the signal that you want to extract, you also have to make sure that the local oscillator is variable as well. Okay, so you have to consider the fact that the local oscillator can span different ranges. So there's two different considerations here, right? So for AM radio, the typical ranges are between 540 and 1600, and your intermediate frequency is 455. That's standard. If this is the typical case, all right? This is the typical case where if your local oscillator is larger than the carrier, then what's going to happen is that if you add, basically what's happening here is that you're adding the local oscillator to each of these, right? Because that's what it's the intermediate frequency, not the local oscillator. You're adding the intermediate frequency to each of these so that you generate these frequencies. And what I'm computing here, this is the ratio. So what this gives you an idea of how much the frequencies span. So this gives you a factor of 2, meaning that between 995 to 2055, there's a factor of 2 that you want to cover. The range is about a factor of 2. Okay. This is another situation where if the local oscillator was less than the carrier, then you have to make sure that you subtract by the intermediate frequency, right? So in this case here, what you're doing is you're subtracting by the intermediate frequency, and then you're doing this as well, okay? Now, if you took the ratio between the two, notice that the range is actually a lot higher. If it's a lot higher, that means that the range of your local oscillator is going to be quite large. It has to span between 85 to 1145. That's actually a lot bigger range than the previous one. So the longer your range is for your oscillator, the more expensive it's going to be. So you have to decide, which range is most suitable or what the conditions are, right? So higher, this means that it's more expensive, because that means you have to design an oscillator so that it spans a larger range of frequencies, going from 85 to 1145, in comparison to 995 and 2055. So there's only about a 2 factor, and then the one at the bottom, if you have the next situation, there's a factor of 12. So depending on which situation that you have, your local oscillator may be cheap or expensive to manufacture. Okay, so you have to take that into consideration as well. So let's see here. So the tunable RF section, so this here. So if you want to figure out what the performance is of your superheterodyne, what people usually do is that you rate it by the way it rejects the image frequency. So the better it rejects the image frequency, the better performing the superheterodyne receiver would be classified as. Okay. So also what some people do is that to improve reception, they usually have multiple intermediate frequency stages. So it's actually, so when you have multiple stages, it's actually a lot, you can make each of these cheaper, so that instead of having one expensive unit, you can have several cheap units, such that it pretty much does the same performance, if not even better. So it actually does, and I won't go into it, but it does improve reception if you actually have multiple intermediate frequency stages. So you'll have one local oscillator frequency that's tuned at a certain amount, and then you have another one that is tuned at the desired intermediate frequency that you wish. So there's 2 stages. So there's 1, and then there's 2, and then after the second stage, you go ahead and demodulate. So it actually will perform a little better if you have multiple stages, and you can make each stage cheap, so that the overall the overall performance is better. So you can do it like that if you wish, but I won't go into that for this course. Okay, so we have introduced the superheterodyne receiver as an architecture that takes a frequency divided multiplex signal and extracts out the station or the carrier signal that you want to, or the carrier frequency that you want to extract out, and then you can go ahead and listen to it or examine what the contents are. Okay, so we've designed it in such a way where you're getting the desired signal and you're making sure that all the other signals don't factor into the demodulated signal. Okay, so that's what we designed. So this is your basic superheterodyne structure. All right. So we're going to go through each individual component just to make sure that we are on the same page. So this is your frequency divided multiplex signal coming in, and then you have what's known as an RF stage. So this is a tunable bandpass filter, okay? And it's also realizable too. It's not high grade, okay? So this is your initial filter to make sure that the image frequencies, right, are attenuated. So FIF, the intermediate frequency is, not intermediate, sorry, the image frequency is attenuated. So you want to make sure that the spectra that's located at the image frequency, you want to make sure that that goes away, but everything else stays the same, okay? And then you have a local oscillator. So what you're doing here is that you are mixing the signals so that your desired channel or desired signal will be converted down to the intermediate frequency. Okay. Notice that the tuning is chained at both the RF and the local oscillator stage, which makes sense, right? Because as you're tuning the carrier frequency, you want to change it so that the bandpass filter is centered at your carrier, and then you're removing the image frequency. So both of these are, of course, the same. It makes sense to make these in parallel, because as you're changing the carrier frequency, you want to make the bandpass filter move, as well as changing the local oscillator as well. Okay? So you're mixing the incoming signal so that it goes down to the intermediate frequency, which is totally fine. Okay? And this is the intermediate frequency stage that we talked about. Remember, this is a bandpass filter that is fixed in frequency. So this means that it's only designed to filter a certain, certain passband or a certain center, and that is centered at the intermediate frequency. Okay, so this is also cheaper to do. So you can make this as high quality as possible, but if you make the center frequency fixed, then it's pretty cheap and it's realizable too. Okay, so how can we build a tunable RF stage? So I'm just going to bring you back to the circuit that we talked about in the past. So this is a parallel resonant circuit. We have a resistor in series, and then it's in series with inductor and a capacitor in parallel. So I'm not going to go through the math, but this is actually what is generated. So this is what the transfer function would be, and then we have what's known as a quality factor, and this quality factor controls the bandwidth of the. So you can think of, so this is actually a bandpass filter. Okay, this quality here that actually controls the width of the passband. Okay, and then the resonant frequency, you can think of that as the frequency, you can think of that as the carrier frequency, the center frequency, or where you actually want to filter out. Okay, so notice here that we can actually change the width by changing the quality. Okay, usually it's impractical to have a variable resistor. It's actually quite expensive, and if you actually were to put this onto a PCB, having a variable resistor actually takes up a lot of room, and it's actually not a good thing. So what people do instead is they vary the capacitance instead, and there's actually a lot of different solutions, such as variable capacitors or varicaps, or there's a lot of different solutions that will actually achieve variable capacitance. It's actually a lot cheaper to vary the capacitance rather than vary the resistance. The resistance is actually, even though it's easier to do, it's actually much more expensive to manufacture, mainly because it takes a lot of room on your PCB. Having a variable capacitor actually takes less room, right? So that's the one I wanted to talk about. If you change the capacitor value, what's going to happen here is that Q changes, and therefore the passband changes. That's what's going on here. Okay? So as you change the quality, right, as you increase the quality, the lower and upper portions of your bandwidth, they also increase as well. So that means that your bandwidth also increases. So you can actually, this is just an example where you can actually realize a tunable RF stage or a tunable bandpass filter just with a simple resonant circuit with a resistor and in parallel, in series with a parallel inductor and capacitor. Okay, so let's see. Actually, I don't have much to do left. So it's actually just a bunch of it should be a bunch of pictures from here on in, and then I'll take a break and then we'll do the tutorial. All right. So here are some filtering requirements for RF receivers. So this is I'm just going to talk about just some further comments. Okay. So what this is talking about here, selectivity is achieved at the intermediate frequency stages, working at a fixed center frequency using special filter technology. So that's pretty well known. Okay. So the radio frequency filter, right? So this is the bandpass filter that we talked about. So this is the bandpass filter. It should have a sufficient attenuation at the image frequency, which is at twice the intermediate frequency with respect to the center, which we already know as well. Okay? The final intermediate frequency stage should have sufficient selectivity to effectively suppress neighboring channels. So what you can do here is not only can you make it fixed, you can also make it slightly variable just to make sure that you can filter out as much noise as you can. So sufficient selectivity means that it doesn't have to be fixed. You can have maybe plus minus a couple of kilohertz, and that's also cheap to do as well. Okay, so image rejecting is one possibility to reduce the radio frequency filter requirement. So if we can actually take a look at I filters and Q filters. I'll talk about that soon. But we can actually introduce this into the mix to actually increase or better, have the R filter perform a little better. Okay, so what we can do here is, in general, a radio frequency signal is actually a complex valued signal. So remember what we talked about, where when you had a quadrature amplitude modulated signal, where you can have two different signals that are modulated together in the same channel, but one is real and one is imaginary. You can make it so that one is actually imaginary and the other one is real. So you can actually, you can represent a radio frequency signal such that there's a real component and an imaginary component. Okay, so you can actually represent it like this. So actually, let's go backwards a little bit. Okay, so this here is what we already know. So this is a band pass signal. This is what we know from the past. I covered this already. So this is band pass signal. So let's actually go backwards. Let's actually go backwards instead. So what you're going to do here is that if you take x of c of t, which is real plus imaginary, and if you multiply by e to the minus j omega c, right? This is equal to cosine omega ct plus j sine omega ct. Okay. Now, if you actually expand this out, okay, so this here becomes over here, and if we actually just take the real component of this result, you will get this guy here. Okay. Just if you actually go ahead and do the math, right? So we can represent a bandpass signal as this representation here. So you have your complex value signal, you multiply by e to the j, which is cos. If you go ahead and do that multiplication, if you take the real component of that, you will get the signal. Okay, so why is that actually important? And it's important because it actually talks about different receiver architectures, which I'll cover next. So you may consider your bandpass filter, as I talked about, it's a quadrature amplitude signal, amplitude modulated signal, where the real and imaginary components represent the in phase and quadrature components. So the in phase means that it's just it's modulated by cosine, and the quadrature components mean that it's just modulated by sine. That's really what it means. So in phase means cos, and quadrature means sine. That's really what it means. So that's cool. All right. So in general you have a bandpass signal. So you can think of your signals over the air as multiple bandpass signals, right? They're at some center frequency, which some particular bandwidth, and you can represent them using this equation. So you can think of the real component as, I guess, the left channel, and you can think of the imaginary component as the right channel. So so there's two signals that are being transmitted over the air that are, different from another in terms of, left and right channel, I guess. So you can think of this as, it has, this spectra like so. Okay. So if this is the spectra for your complex valued signal, okay, then if you were to do a bandpass signal, if you actually do the modulation, then you'll get something like this. I'll actually talk about this more later when we talk about FM, but for now, just take my word for it that this is what you get. Okay? Okay. So due to the complex valued structure of that particular bandpass signal, the upper and lower sidebands are actually quite unique. So they're two different signals, all right? So what you're going to need in general is you're going to have a radio frequency receiver. So let's assume now that what we assumed in the past was everything was real value, but in general, you may have, actually, what's going on here? Sorry. Oh, okay. You may have, signals that are, complex in nature that actually have two different signals. So what you're going to need is you're going to have a receiver such that it will demodulate both portions separately. Okay, so you have a bandpass filter. You've got a bandpass signal. You have the RF filter that filters out. So this is your bandpass filter. This filters out the particular signal that you want, and then you need this. So this generates your real signal, and this generates your imaginary signal, or the imaginary component of that. Okay, so you have your, you've got your cosine wave, right? And you want to modulate it with cos, right? Remember, this is demodulating using double sideband suppressed carrier, right? So this is demodulating. right? You put a bandpass filter and then you get the real component. And then if you want to get the other one, you just multiply by sine. We cover this with quadrature amplitude modulation. Okay, so you put your signal through, multiply by sine, and then you get the imaginary component instead. So that's what's known as I and Q, or in phase and quadrature. Okay, so what this is doing here is that it's performing quadrature radio frequency down conversion. So it's actually, so this signal processing here, this does the heterodyning and the this does the heterodyning and all that stuff, heterodyning and demodulation and all that. Not demodulation, but the heterodyning and everything else. Okay. So the purpose of what this is doing here, if you have your, you've got your local oscillator here, so it's doing a down conversion so that remember, this is getting your intermediate frequency, I guess, right? So you're getting the actual intermediate frequency, you're putting everything down to that intermediate frequency, and then you're using the signal processing block to, to do everything else. Okay, so there are two different types of radio frequency receiver structures that work with complex, bandpass signals. There's one which is called the zero intermediate frequency receiver. It's also what is known as a direct or homodyne conversion receiver. The reason why this is because it will down convert your signal directly to baseband, so there's no intermediate frequency at all. So what this does is that it will, instead of this being a bandpass filter, it does it using low pass filtering instead. So it modulates it in such a way where the local oscillator is in fact the carrier frequency, and then you apply a low pass filter, and then you actually get the real and imaginary components as is. So there's actually no heterodyning at all in this case. It actually just does it, and it gives you the actual real and imaginary components without doing any heterodyning. Okay, so that's one particular circumstance. The advantages here is that it requires less hardware. You don't need any heterodyning stage. There's no intermediate frequency filter and all that. There's no additional hardware. Okay. There's also no image problem, which actually makes sense, because if you modulate with the carrier frequency, you get a copy of the spectrum plus that 2 omega c, which you could filter out. Okay. Low pass filter is sufficient for filtering, so you don't need a bandpass filter, which is more expensive to manufacture. Okay. The intermediate frequency filter and subsequent stages are replaced with low pass filters, and they can be easily implemented with monolithic ICs or integrated circuits. So that's actually a good advantage. Okay. The disadvantages are that we may have a point where the omega c is not exactly equal. Okay, so you're going to need PLLs and all that stuff to make sure that you're modulated at exactly omega c. So this is what it means by output leakage, which means that the omega c may not be exactly the same as what is coming in. So you're going to have that frequency mismatch, which we talked about in the past. Okay, there also may be DC offset errors too, which can factor in everything. There's also what's known as flicker noise, and that flicker noise is dependent on this as well. Okay, so you can actually flick back and forth in between the desired carrier frequency and and other frequencies as well. Also, there is something which is what's called an IQ mismatch. So this happens if, remember, you're using the carrier frequency to demodulate the real and imaginary components, and so what's happening is that when you're doing the phase shifting to get the sinusoid, that phase shift may not exactly be 90 degrees. So you may not get a perfectly sine wave as well. So what this means by IQ mismatch is that the real and the corresponding imaginary components may actually not be the same in comparison to what you did before you generated them. And then even order distortion, I'm not quite sure what that actually is. I'm not sure what that's here. So you can ignore this for now. I'm actually not quite sure what this is. Okay. So just one last thought before we'll take a little break. Okay. So software-defined radio, this is the last lab that you'll be seeing in this course. Okay. Basically what's happening is that what we've seen so far is you use traditional electronics to demodulate amplitude modulated or frequency modulated signals to listen to the station that you want. Okay? So what software-defined radio is that all that demodulation process is actually done through software. So what you're going to do is you're going to take your radio signals that are coming over the air, and then you're going to use you're going to take those signals and convert it into digital by using high-speed analog to digital converters. And then you do all the demodulation done digitally. And then all the demodulation and all that is done through actual software and through Simulink and some hardware and mixed into it as well. But the point of software-defined radio is that all the demodulation is done through digital hardware, so FPGAs and DSPs and all that, in comparison to using standard electronics that we've seen already. Okay? So the receiver is an ideal software-defined radio where you're sampling the frequency division multiplex signal or the antenna, whatever's coming through the channel, whatever's coming through the air, using high-speed analog to digital converters. And then what you're going to do is you're going to demodulate the signal completely through software, either through a computer or through an embedded system like Simulink or an FPGA or whatever have you. So the sampling of your audio signals is converted digitally using A to D converters, and then the demodulation is done completely through software. All right? Sorry. So with today's technology, it's not feasible to digitize a received radio frequency signal at such a high sampling. Remember, this is a continuous time signal, right? So if you want to be able to listen to your signal with very high quality, you're going to have to sample the signal with a very high sampling rate. So it sounds like you're listening to it with a normal standard analog, demodulator. Okay? So you have to have high quality, analog to digital converters to do the same thing. Okay, so it's actually, with today's technology, it's actually not feasible to do that, unfortunately. So what you do is you're going to have some hardware that's actually going to be at the front of the receiving end. So you're going to have some hardware like an FPGA or DSP that'll actually help you transform it in such a way that it'll actually be easier for the computer to demodulate. So you have a hardware front end that shapes the received signal and converts it into an intermediate frequency. So what's going to happen here is that you'll actually perform some heterodyning, or you're going to take the hardware front end that's actually very sophisticated like an FPGA, and you're actually going to convert down to the intermediate frequency. And then you can use this intermediate frequency, which is a lot better to actually sample at. Because remember, if you have a carrier frequency that's in the megahertz, you're going to have a digital analog converter that'll sample in the megahertz too, which is bad. So you want to use some sort of hardware front end to take that signal and demodulate it down or convert it down into a realizable intermediate frequency so that you can have slower analog to digital converters that actually sample that content for you. Okay, and then these hardware front-end units are what are known as universal software peripherals. Okay, so that's the hardware that is used to perhaps demodulate or heterodyne down to the intermediate frequency. Okay, so many software-defined radios are based on the zero intermediate frequency receiver architecture. So you've got a bandpass signal coming in, you also have, this is your bandpass filter, and then this is what is known as a low noise amplifier, LNA. So the purpose of this is to basically amplify your signal, but then but not amplify the noise. So that's what low noise amplifier is. So if you have low power signals, it tries to amplify those signals so that it becomes high power, but then it tries to minimize the noise being amplified as well. Okay, and then this stuff here is what we've seen already in the past. So this here is just your zero IF receiver architecture. Okay, so then once you get the real and imaginary components, you put it through an analog to digital converter, and then you have a DSP that'll actually go ahead and do the rest of the work for you. Okay, so in your lab, you're going to be using what's known as the EDIS Research N210 Universal Software, radio peripheral. Okay, so basically here, this is what you've already seen. So this is your zero IF receiver. Okay, and then an FPGA will be used here to go ahead and demodulate your signals and then do the rest of the work. Okay, so you've got so this is your universal software. So this is your this is your zero IF receiver. So there's cutoff frequencies of 40 megahertz. All right, and then you've got analog to digital converters that will take your signal and convert it into digital, and then you have an FPGA that'll do the rest for you. So you have a digital down converter here, and the reason why that's the purpose of the reason why that's there is because it will convert your your signal now, which is at a very high carrier frequency. It converts it down so that it simulates it so that it brings it down to an intermediate frequency. And then once you have this, then you take the signal, which is mixed down or heterodyne down digitally, and then you can go ahead and use any computer to go ahead and further demodulate the signal and get the actual audio signal you want. So you can use MATLAB Simulink or GNU Radio and so on and so forth. So this is what I talked about. So in experiment 4, you're going to be doing this particular thing. You're going to actually be demodulating live radio signals using a sampling frequency of 200 kilohertz. Okay, so the last structure that I'll talk about, then we'll take a little break, and then I'll do your tutorial questions, and hopefully I'll get out of here within a half an hour or so. There's the last structure, which we have what's known as a low intermediate frequency receiver. So what this actually does is that it mixes the two together. So you have the extreme end where you have a zero intermediate frequency. So there's no heterodyne. It goes right to the baseband. What this does is that it tries to heterodyne, but it makes the intermediate frequency very, very small, or very, very small compared to the original carrier frequency. And the reason why you do that is because it tries to combine both advantages together. So it tries to combine the advantages of your zero intermediate frequency receiver and the super heterodyne. So it's a non-zero, low, or moderate intermediate frequency. So it tries to combine them both. And here's my last slide before we take a break. So this is just a breakdown of how all the receivers compare. So you have your super heterodyne receiver. So the advantages is that it's immune to DC problems, right? Also, you have a wide range of what you can select in terms of the actual carrier frequencies. The disadvantages is that we've seen this already. So there's the image frequency, right? So you have to design, your bandpass filters such that it filters out the image frequency. It can get complex. It also doesn't deal well in terms of noise. Also, if you want to put this in a software-defined radio, you're going to have high-quality discrete components, and there's also nonlinear behavior you have to consider as well. For the zero intermediate frequency, it's very simple. Also, you can put this into integrated circuits, no problem. Unfortunately, there's also a strong DC leakage. There's also the IQ mismatch that we talked about as well. There's also flicker noise, and for the low intermediate frequency, that's a little hybrid between the two. So there's no DC leakage. Very simple. It requires less high quality, discrete components, and then you also have to deal with the image frequency as well, because that actually tries to combine the process of super heterodyne and zero IF together into one stage. Okay, so that's it for theory, and then we'll take a 10-minute break, come back. I've got 3 questions to solve, hopefully take 20 minutes, half an hour tops, and then we can get out of here.